Hi everybody, it's Matt here, and today we're going to talk about thermodynamics. Specifically, we're talking about something called PV diagrams and how they relate to heat engines. Now, before we go on, I have a confession to make. When I was first learning about thermodynamics, I always had a difficult time really connecting to the material because I didn't really see how it applied to the real world. I learned all the formulas. I learned how to solve the problems, but I didn't really see how what we were learning about was really applicable. And so hopefully from this video, you'll get a better sense of how it actually works. So a couple of the equations that we're going to refer to. The first one is just a statement of the first law of thermodynamics, which is U, or delta U, is equal to Q plus W. In this case, delta U is our internal energy of a gas. Q is the heat that can transfer into or out of the gas, and W represents the work that can be done by the gas on the system or on the gas itself. The second formula states that work done by the system is equal to negative P delta V, where P is the pressure the gas is under, and delta V is our change in volume. Now, nothing made it more clear to me that I didn't really get what was going on in thermo than the day that I walked into my lecture hall and the professor proceeded to put this diagram on the board. And no sooner did he put that diagram on the board that he proclaimed to the entire class that this was a picture of an engine. Now, I don't know about you, but when I look at this, that doesn't look like an engine. This looks like an engine. This looks like a box. But what we're going to see here is this actually is a diagram of something called a heat engine. And a heat engine is something that's going to take in heat and transform that into useful work. Now, to think about that, this diagram as being a heat engine, I want you to imagine a situation where we start with a gas that is in the state noted by A here. So at point A, you'll note that we're at a fairly low pressure and a fairly small volume. The way we could demonstrate that is imagine we've got a piston right here, and this piston, this cylinder is filled with a gas. And this piston is free to slide around, and so this gas, all these little particles bouncing around inside the piston, would cause that, that piston to slide upwards if it wasn't being held down by some sort of pressure. Now we can imagine that what's holding this piston down maybe is like a small weight. So there's one little small weight sitting on top of that piston, and that's providing a downward pressure which keeps the piston from sliding upwards because of the gas particles bouncing around inside it. So it's at a relatively small pressure because it's just got a small weight on it, and you can see that the gas is occupying a fairly small volume. So this represents state A. Now what would happen if we wanted to proceed to state B? What would happen if we wanted to change our gas from what it looks like here and move along to B? So what would this look like to get to state B? Well, you can see as we move from A to B, B is really, it's at the same volume. We can draw a line down here and note that A and B are at the same volume, but we've now increased the pressure. So if the volume is the same, well then the piston is still in the same position. It's still that relatively small volume. And the gas is bouncing around inside, but somehow this gas is under more pressure. So if it's under more pressure, that must be because, well, there's more weight potentially pushing down on it. So imagine that we've added an additional 2 blocks. So now we've got 3 blocks maybe sitting on top of this. So that extra pressure pushing down on the gas has to push up to support those blocks. But you see, we can't just add more weights without that gas becoming compressed because this piston can slide up and down freely. So something else must have happened in the process of going from A to B. If we're increasing the pressure and yet the volume isn't becoming compressed, those particles must be bouncing around a lot faster and colliding with the container much more rapidly, many more times per second. And so the reason they're doing that is because we must have added heat. The only way that we could increase the pressure and keep the volume the same is we must have added some energy to those particles, get them bouncing around faster. So you can see we add heat to proceed from A to B. So what then would have to happen to go from B to C? Well, B to C, you can see we're still at the same pressure here, but we've actually increased our volume. If you look down here, we're actually moving along the volume. So to get to state C, that means the piston must have slid upwards. And since we still are at the same pressure, we still have our same 3 blocks on top. Now those particles are bouncing around and keeping those blocks from falling down, providing the upwards pressure to keep them from coming down. And so you could ask yourself, well, if the gas is going to expand and carry those blocks upwards, that means those particles must be bouncing around even more and more quickly. If they're somehow traveling that greater distance, the same particles are covering that more distance and still supporting those weights. So the only way that could happen is if, again, we somehow added heat to the system. We must have heated up the system again to get those particles moving even faster to make this possible. So how then do we move from state C to state D? Well, state D, you can see, is at the exact same volume as state C. So the piston is still way up here. It's still at the same, occupying the same volume as state C. But what's changed is we've now dropped down in pressure. We've decreased the pressure that is on our system. So that's, in our analogy here, that's like we're down to just 1 block. Now this is important to note. What's happened here is between state C and D, we had to take 2 of these blocks. We had to take 2 of these blocks and remove them in order to get at this lower pressure. Now, at the same time, if we're going to have the same number of particles bouncing around in the same volume, but only supporting a smaller pressure, a smaller downwards pressure, those particles must have actually slowed down. Otherwise, if they're still going around as fast with less weight, then the piston would slide up further. So if they're slowing down, then we must have actually pulled some of the heat out of the system somehow. And so that some of the heat has come out. And then the last thing we're going to do here is we're going to slide along this diagram, and we're going to move from point D, we're going to slide over here to point A. And A is right back where we started. So small volume, small pressure. 1 block sitting on the piston back where it started. And the gas is right back in that original state. Now, to get from state D back to state A, if we're supporting a small weight over a smaller volume, those particles must be moving more slowly, and so we're pulling more heat out of the system. So this is it. We've just gone through a cyclical process. We started at A, moved to B, then C, then D, and back to A. And along the way, we added some heat at one step, added some heat at another step. Later on, we took some heat out and took some heat out. Now, it's important to note that I'm just writing Q here. I'm not saying anything about the amounts of heat that are going in or out. I'm not saying more or less heat is being added. But what's really, really important here, what I really want you to notice is what happened right here in moving from step C to step D. Because we took some of these weights off of our piston. And this is work. We initially started off, you think of these pistons as like an elevator. We started off with 3 weights on the first floor here of our elevator, way down here at the first floor, and then we lifted these 3 weights up to maybe the top floor of our elevator. And that did work. Now, it's a really simple example of just lifting some blocks. It doesn't sound particularly useful, but this might be, like in this other example of an engine, pumping a piston, which is driving an engine in a car or something else. So as this piston slides upwards and pushes against that heavier pressure or greater pressure, then you can see that we're doing useful work. So what does this all mean? In a PV diagram, as long as we proceed in this clockwise direction, then we have an engine that's doing work. And that doesn't matter what the shape of the PV diagram takes. It could be a simple square or rectangle like we have here. It could be triangular, or it could be all sorts of curves and things like that. As long as you proceed in a clockwise fashion, then your engine is doing work for you. Now, you might want to know how much work is being done. Well, remember that the work being done is equal to negative P delta V. Well, if we look at our diagram here, in this example of our rectangle, this side of the rectangle right here is really noted by pressure. And this side of our rectangle is volume. And if work is pressure times volume, then work is also in this case equal to the area underneath the curve. Okay, that's it for me and heat engines. Hopefully that makes a little more sense. Take care.